All right.
Again, thank you very much for the introduction and the invitation. As Helen said, my background is quite diverse and my professional experiences are quite diverse, but at the core of all of these experiences has always been artificial intelligence. I did artificial intelligence for my graduate work. I worked with several different applications in the biomedical space, which still remains a passion for me, biomedical science. But as this field progressed, we've seen the tremendous intersection between large compute and AI. And that's how that intersection, that interest in large compute led me to the Oak Ridge National Lab, which has always been leading in high performance computing. And I have been fortunate enough to have a wonderful career at Oak Ridge and now lead this particular division and the leadership computing facility. So today I will spend some time talking about AI. And I will, this is an outline. I will spend just a few minutes giving a quick overview of AI. What is the definition, the historical evolution of AI, and where we are right now. I will spend a few more minutes on Oak Ridge Leadership Computing Facility and some of the latest addition with the Frontier supercomputer and how we are deploying Frontier to support AI and data-intensive computational loads. I will highlight some of the activities, the scientific activities in our portfolio as they are right now. And I will spend a substantial amount towards the last part, thoughts on challenges, potential, the future of AI, by doing a little bit of reflection. Because as I said, I've been in this field for several decades, and I always joke that with all the excitement that exists out there for AI, I'm old enough to have seen the different phases, the rise, the stagnation, and now the renaissance again of AI. And there are quite a few important lessons learned from my generation that is important that we share with the new generation of AI evangelists. So that's going to be the philosophical part of the presentation. So let's start with a quick overview of AI. What is artificial intelligence? Keep in mind that this is a field that originated 70 years ago. There is nothing new about AI in terms of the concept. And the concept...
The screen sharing is paused for some reason. Okay.
And the concept has always been, can we build machines that mimic human intelligence? That was the overarching goal. Oops. Okay. Human intelligence. So when we talk about human intelligence, a fundamental question is, what is the difference about being intelligent versus behaving intelligently, right? And the different flavors of AI sort of try to capture throughout the years our evolution. Everything started with systems that act like humans. That was the first attempt, and that combines, that has the notion of behavior. So when we try to address that aspect, that's where we got. We got with the Turing test that I'm sure you heard that before. That was the pivotal test to say, have we made the first step towards artificial intelligence? And what is the Turing test? The Turing test involves three components. It involves the examiner, it involves a human, and it involves the machine, the computer. So the question is, the interrogator, when he or she asks a question, and they get a response from both the human and the machine, can the interrogator tell the difference? Who responded? If the interrogator cannot tell the difference, That's the first step towards artificial intelligence. And that's how everything started with AI. So passing the test, though, does not truly show that the machine was thinking. It simply demonstrates that it can mimic the human behavior. So the evolution we've seen throughout the years in terms of artificial intelligence can be mapped into 3 distinct phases. Everything started with just defining what we're trying to achieve. And with artificial intelligence, we want something more than simply mimicking human behavior. We truly want to build a machine that can not only memorize, learn, think, and reason like a human. A machine that can take all the stimuli from the environment and adapt to the environment the same way humans have demonstrated that ability. So that is the overarching goal. But when we started in the 1950s, the first way to accept that, to move towards that type of machine, was trying to encode human knowledge into a set of rules. That was the first generation of artificial intelligence systems. We call them expert systems. So imagine trying to build a system that can do medical diagnosis. You go to the physician and you ask them, when you have to do a medical diagnosis in this particular domain, what do you do? And they can capture in writing for you the different rules. If I see this, then I determine that. If this, then that. Imagine a whole bunch of rules that are captured into the expert system. That was the first generation of AI. Interesting, but not necessarily an approach that it is easily scalable, because for every decision, you need to get the expert in the loop to give you the set of rules. World changes, rule change. This is not a scalable and sustainable effort. So the next generation was what we call machine learning. It happened in the 80s. And all of these coincide with advances in computing hardware, as well as mathematical advances in terms of algorithms. Machine learning came and said, this is not sustainable in terms of just capturing everything in rules. Is there a higher level of abstraction that we can achieve? A typical example, we want to build a system, a computer, that can differentiate different types of fruit, right? You show an image and you say, is it an apple? Is it a peach? Is it a banana? What is it? You can have the human give the rules that says, if it is yellow and has that shape, it's a banana. If it's round and red and smooth texture, then it is an apple. If, and you go through all the combinations. Or you can have the expert say, you don't need to capture all of these rules. Just focus on certain attributes that we know are important for doing this classification as human beings. We typically look at the shape, or we look at, the color, the texture, whatever it is. So try to identify what are the important features, and then throw data to the system and let the system come up with the rules. That is machine learning. The human is still in the loop because it provides some insights that you need to focus on these types of features, on these types of attributes. And after that, if you have enough data, enough images of fruits with what kind of fruit it is, don't worry about coming up with the rules. Just throw them in the system and the computer will come up with a solution. And indeed, that's what happened with machine learning. We developed several systems that were able to do these kinds of classifications, including medical diagnosis, by having the expert, human, provide some general, attributes. I was always in breast cancer imaging, breast cancer diagnosis. We knew that we're looking for masses, we look for calcifications, we look for architectural distortions. They have certain shapes, they have certain brightness, they have certain sizes. So we knew that the important features were these things that I covered. By giving enough mammograms, breast images that had examples of masses, calcifications, architectural distortions, or nothing, and the appropriate labels, we trained systems that could do that with sufficiently good performance, often outperforming the typical radiologist or medical expert. Not always, because clearly there is so much you can achieve with this. Experience, lengthy experience matters in certain tasks. Not everything in life is about classifying fruits. But the true revolution in artificial intelligence happened exactly 10 years ago, around 2012, after several years of stagnation in the 90s and 2000, where we said that even that aspect of machine learning is not truly sustainable, because for every task, we need to be identifying the appropriate features or attributes. And maybe there are certain attributes that are important that we are not aware of. Can we learn from raw data? So this is the difference between what we call traditional machine learning versus what we call now deep learning. In traditional machine learning, a human needs to sit there to do handcrafting of the different features. If we're trying to classify a cat, we need to focus on different shapes, eyes, ears, mouth, and say, oh, it is a cat versus a tiger versus a dog versus whatever. But in deep learning, this end-to-end pipeline is completely mastered by artificial intelligence. So what features are important? What levels of abstraction are important? We have developed algorithms that can do that. And that happened in 2012, and it started actually with computer vision, exactly, trying to identify objects in different images. Is this an image of a cat? Is this an image of a car? Is this an image of a sunset? Whatever it is, where the algorithm was able to develop these levels of abstraction, going from identifying first low-level features, let's say edges, to learning mid-level features, to go all the way to high-level features like eyes, nose, mouth. Therefore, it is a face. So this is where the major aha moment happened in 2012 with that example. And in that example was enabled by creating neural networks that were more and more complex. And by more and more complex, we mean networks that have more and more layers. And you will see an example later on. So this is another way to conceptualize the difference between machine learning, which still exists, versus deep learning. We have effectively replaced the feature extraction processor with AI itself. Everything happens in one-stop shopping. That opened tremendous possibilities in terms of deploying artificial intelligence across a number of different tasks and projects that before we were not even considering, because we didn't have the vast volumes of data and the humans to provide the rules or to identify the features. So why that resurgence in 2012? What was the critical point? That was the time when we had true convergence among three things. First of all, big data. This is the digital era. We generate data in massive amounts. In terms of images, think about all the content that exists right now on social media, and it is generated on a day-to-day basis, content over content. Think about different text documents, again, that exists on internet with Wikipedia and everything else. Think about data that we generate from sequencing, genomic data that is generated on a daily basis. There is a tsunami of data that is generated and sits there. Actually, data generation is not the problem that our society faces. Data storage and management is the true challenge because not all data is valuable data. We don't know if we would need it now or later on, and we are drowning in data. The second enabler was new hardware, the graphical processing units, which helped with accelerating computation, and of course the supercomputers. And the third one, algorithms. Algorithms and optimization techniques that before computationally were not really feasible. But as we brought data in and as we brought powerful hardware, certain algorithms that we had conceptualized years ago, decades ago, now became truly feasible. And that's the convergence that led to that revolution in 2012. So this is the new wave. And my prediction is that this new wave is here to stay because of these enablers. And that is another way to see how that important point in 10 years ago has led to, has helped us overcome that stagnation point. We had reached the point where we could not truly improve the performance of the existing AI systems. And there wasn't much amazing technology being developed, just developing another machine learning algorithm for another narrowly defined task. But we have seen that over time, as the amount of data that is available increases, so does the performance of these AI systems. So we were able to overcome a certain bottleneck that we had faced with machine learning. And now think about why data is important. With more and more complex algorithms, that means that we have a vast number of parameters that we need to estimate in these models. The more the parameters we need to estimate, the more data we need. The better we estimate, the higher the performance of the model. And that's why this dependence of deep learning on vast volumes of data. Yeah.
Early on, you made a distinction between learning and thinking. Is there a test beyond the Turing test that determines whether or not a machine is thinking?
I will show you some examples, and I will defer this response to you if it is true thinking. I don't believe we have reached that level of what is known as super intelligence, but certainly we have made a lot of progress. And I will show you some examples, and I will try to highlight that aspect. So these are two very specific problems that we use as benchmarks in artificial intelligence to keep pushing the performance of the different algorithms. Because this is a community that works on different algorithms, different approaches, but we all want to benchmark the performance of our systems on the same data set, same problems, so that we can do the apples to apples comparison. As I mentioned earlier, computer vision is the area where we have some of the most well-known benchmarks in AI community. And you can see how for many years we were hovering around the 30% classification error. And then with the introduction of deep learning, we keep improving the performance as we move forward. And actually in 2015, for one of those benchmarks, we broke the barrier of developing a system that has better performance than human. Where for this particular benchmark, the human error was at 5%, and the AI model at the time broke that barrier. The other application is in protein folding. For those in computational biology, understanding and simulating protein folding is a well-known challenge. And for decades, the scientific community has been developing these large-scale molecular dynamic simulations. With the introduction of AI in, as you can see, in 2018 with AlphaFold and a later generation of AlphaFold, we were able to hit what is known as 90% score, which is the equivalent to what we are getting, what we are confirming experimentally. So these are some of the examples that are considered as highlights of how much progress suddenly we made with the introduction of deep learning in problems that puzzled us for quite some time. And we had, as I said before, stagnated. And this is what's happening right now with artificial intelligence, what is known transformers or language models. These are extremely deep neural networks that are very complex. And initially, they were developed for analysis of text data, speech, sequencing data, sequential data. And subsequently, these models have been applied to a large number of problems where you can say the data is like sequential data, like genome data. And we've seen that by developing these transformers with the ability to do self-attention is they can apply different weighting schemes to different parts of the sequence of the data. These models have shown a tremendous ability to capture context. And I will show you how that translates to an application that probably you have experienced, but you have not really realized it. But before I go to those examples, this is what's happening right now. We care about developing these transformers, these large models that have the ability to ingest large volumes of extremely diverse data. And after these models have been pre-trained, the different communities take them and they just fine-tune them in their own space with carefully curated data. So for the first part, for what we call pre-training, we throw to these models all the data we have available. We don't know what the data is about, we just throw images, text, whatever it is, and we pre-train. Just one way to pre-train, for example, for natural language processing. We give it text. The neural network captures the text, and the actual task that we ask the neural network to do is, for us, we mask words, we give it a passage, we mask words, and we say, tell me, what word is missing there? For this kind of exercise, we don't need labels. You know what word started with the text, just mask things. And by training this network, the network learns to capture the context across the whole passage. Then with this thing pre-trained, you say, I have a pre-trained model sort of comprehends language, but I want to apply it in my very specific application domain to ask questions related to biology or related to medicine. It was trained with very general text. How can I make sure that it can learn contextual information that is important to the specific field? Then I can use my small data set that is very carefully curated by the experts to enable this large model to pivot and improve its performance in this very specific application domain. So this is what we're seeing the community doing right now, leveraging large volumes of data that seem often irrelevant, but to do some initial formalization of this neural network with subsequent fine-tuning exactly for the task at hand. So this is the current thinking of the scientific community. We cannot be developing AI solutions for every little thing we want to do. We would like to move towards big, powerful models that then it will take less to pivot them towards different types of activities. Also, there is a lot of interest towards what we call transfer, multitask, and multimodal learning. We, as human beings, we don't learn to do one thing at a time. There is, of course, similar context in a number of different activities that we learn to do. So being able to develop AI models that can do multiple things at the same time, that's an active area of research. The ability to do transfer learning. I learned how to walk, and some of the lessons learned from walking could translate to me running. That's what we call transfer learning. And multimodal learning. Everything in the AI applications for several years has been, I'm analyzing images, I'm analyzing text, I'm analyzing genomic data. But we are individuals who get information from many different types of sources. We can get visual information, textual information. So we want to develop AI models that do multimodal learning. Essentially, we throw into these models different types of data. And now the latest benchmarks show neural networks that over the past decade were able to learn 10, 50, 200 to 600 different tasks. This is part of the continuous progress with this technology. And fortunately, these networks, in order to achieve that kind of performance, they are becoming bigger and bigger and bigger. And that's why the need for a lot of data, even more and more data. AI is data hungry, but also it's compute hungry. And that's why the convergence of the three things I discussed earlier. So here is a fun application. This is one of those applications that emerged in the past year or so with very large language models, actually, which can take a verbal cue and paint a picture. So that's where now your question about intelligence. This is now capturing, not only paint me an apple, but look at the cue here. The corgi playing a flame-throwing trumpet. Paint me a picture like this. And AI produced these two. Here are some examples. Another verbal cue, paint me a flower shop that has these certain colors and a very clean white facade. Then it came up with this picture. Now, I will jump a few steps ahead, and I would like you to pose the question, what does this mean for different, for a certain type of workforce? What does it mean for a graphic designer? Is it a help or is it a threat? These are some other applications. There are so many fun applications that you can actually retrieve them from these papers that are publicly available in terms of, okay, paint me teddy bears, shopping for groceries in the style of Peter. So this is an application domain, or the teddy bears. And they're very, so we have AI actually truly comprehending text, verbal cues, which led, of course, to what I'm sure you all have heard about ChatGPT. This tool that I encourage you to go. It's very easy to sign up on OpenAI and play with it, assuming you will be able to get in because it is extremely popular right now. And this is the idea of AI model that has been trained with a very large number of texts and can generate human-like text when given a prompt. It can write essays, it can write reports, it can write jokes, it can write software code. It can do presentation outlines. Actually, when I played with it, I went in and
make love.
I actually wrote, I gave it a cue and I said, write me a poem. And I said, rewrite Odyssey with respect to leadership computing. And within seconds, it gave me passages that was exactly like Homer's Odyssey, where now Odysseus was leadership computing, talking about the successes and the struggles in terms of the changes in the hardware, the struggles in terms of cloud computing. It was truly impressive. And there are so many examples, people going in and playing, to the point that now one of the major concerns in the scientific community is that when we submit papers, how do we know if the author truly wrote the paper or they had assistance? Because you can go in and effectively ask these kinds of questions.
What about music? Can you take a poetry and make music?
That would be very interesting if you can give data in terms of different music, just like when it does with code, we give lines and lines of software code and say, rewrite that in that particular programming language. I have not seen an example like that, but it would be interesting to see how that can be converted there. it takes time, but you see these advances happening in less than a decade. This is where it is impressive with this particular wave of AI. The other thing that it is actually impressive for me, some people find it extremely threatening, but I find it intriguing, is that, as you know, in science, scientific discovery has the aha moments. It has the aha moments, right? Because we read something, we talk with someone, and there is that spark, that idea. But we have reached the point that there is so much information there that we are all scientists are bombarded with so much information. And it has become more and more challenging to cross boundaries, domain boundaries, which is usually where most of the innovation happens. And you can have a system like that where you throw your idea in there and you say, what do you think? And it can come up with concepts that you say, And actually, there were papers published about that, where GPT was listed as a co-author. And that has created a whole, that is another very heated debate as to whether this should be done, whether ChatGPT should be a co-author that cannot confirm their contributions and they cannot have liability about what they're saying. So there are lots of issues related to policy. But to me, this is an assistant. We're thinking now about so many ways this type of technology, I'm not saying specifically ChatGPT, will become an assistant across a number of activities that may be day-to-day activities, but now we're talking about aspects that are truly about creativity. So now with that premise, let's move it to the Oak Ridge Leadership Computing Facility and how the big compute we have is here to support scientific discoveries related to AI. I understand that you've probably heard about the Leadership Computing Facility for other speakers in the past. The Leadership Computing Facility at Oak Ridge is 2 decades old. In those years, it has a very well-defined mission, defined by executive order, and that is to provide world-class computing to the scientific community, openly to the scientific community, to help them with the most computationally intensive grand challenges. So we're really at the bleeding edge of computing for those scientists who need us the most, who have the most demanding problems. Throughout the years, we have delivered a number of different systems, and starting with 2009, when we broke the petascaling barrier. And a year ago, with Frontier, the system we deployed, we broke the exascaling barrier in the world. And we are very proud about this system.
Are these massively parallel computers especially promising for this application? Is it good to have massively parallel processors?
Exactly. And the systems, when they started, they were CPU based. But in 2012 with Titan, we introduced the accelerators, the graphic processing units, which are extremely important for artificial intelligence. The systems, though, at least up to this point, they are designed to be general purpose systems. In other words, they can support computational workloads that are benefiting by CPU, only CPU, the modeling and simulation workloads. They can do purely AI kind of workloads, but they can also support those applications that benefit from both. And we are seeing a lot of these applications these days that mix modeling and simulation with certain components of AI to accelerate aspects of modeling and simulation. So I would say that the supercomputers, the sweet spot for the supercomputers are exactly these mixed kind of workloads, because you can have this one environment that can help you accelerate both aspects of computation. So the The supercomputers, we typically have the certain benchmarks according to which a supercomputer is deemed number 1, number 2, number 3 in the world. That happens every year. And Frontier, when it launched, was the number 1 supercomputer according to the HPL benchmark, which is a certain type of computation. That was last November. It is more powerful than the next 4 systems in the world. And you can see how powerful this system is. And of course, next year, there will going to be more benchmarks. There is a global competition in the space of leadership computing. That is an area that every advanced nation wants to invest, because pretty much these days, any kind of science is computational at its heart. We've seen this. I will not go into the details of these different spots. We got the number 1 spot for one benchmark. We got the number 1 spot for the AI benchmark. So that gives you a notion of how powerful the system is for the different types of workloads. And in terms of being in the green 500, energy efficiency was number 2. It is a resource for our nation, and it is a resource for the world. This is a computer system dedicated to open science. Everything we do is open science. And because of that, there is tremendous demand for the resource. We have different allocation programs, and the allocation programs are based on open competition. By open competition, it means that we receive proposals from any kind of application domain. There is an external review process with domain experts outside the laboratory and outside UE. And based on scientific impact, computational readiness of the code, we decide the priorities in terms of who will be allocated. We're always oversubscribed. We get 3 to 5 times more applications than what we can allocate for our users. So let me go into, okay, I will try to be faster. In terms of different AI activities, the Oak Ridge National Lab also has invested in the AI initiative, where it works across the different mission spaces to develop and deploy AI solutions. And as you can see, I have highlighted, this is a slide borrowed by David Wamble, who leads the AI initiative at ORNL. And here very clearly he lists the types of applications we have across the lab, that are in material science, in climate science, bioscience, neutron sciences. We have AI deployed across the different facilities to create what we call smart instruments and automation of experimental design. We have AI deployed in energy systems, transportation, for the electric grid, and of course, national security, cybersecurity, and non-proliferation. Absolutely, they are areas where there are large, important applications in AI. Now, there is the application side, but there are also the theoretical foundations of AI that enable successful application. And on the right-hand side of this slide, you see where exactly we are investing. There are some very important aspects that I will highlight in different order. In terms of data collection, we talked about data being very important, but having AI enable the data collection and the data reduction is an important step in the process. So don't think of it that it is only for analytics and for the final decision making, but it is also a technology that can be very useful at the front end during the experimental design and data acquisition. We see we have the notion of the digital twin that is highlighted out there. And this is something that's happening across many application domains. A lot of experiments that happen cannot really scale up easily in real life, right? So imagine if we had a computational model of that system, whatever that system is. How much will we be able to do completely in silico, explore different scenarios, and do it completely computationally without costing or without waiting for certain conditions, experimental conditions to be satisfied? I'll show some examples later on. And then we go into aspects of, well, we have painted a great story about how much is possible with AI, but I have not talked at all about its failures. And AI, when it fails catastrophically. Because it can give you a very confident response, but the response that is utterly wrong. I played with ChatGPT and I said, can you explain to me why bears are so, enjoy so much the moon? And it gave me a whole essay about the bears that live happily ever after on the moon. So it's me who was wowed by the example of, oh my God, I see Odyssey written in front of me about leadership computing. And at the same time, I'm reading this thing about bears living happily ever after on the moon.
Really?
So how we can develop, how we can go back to our scientific roots about mathematical and algorithmic advances that enable us to test the reliability, the robustness of the AI models, being able to do what we call uncertainty quantification. Usually with predictive models, we like to put an error rate, you know, its accuracy is 90% plus or minus 5%, whatever that is. But for a model, globally speaking, that doesn't mean anything when you have to look at the individual prediction. This one prediction in this particular circumstance, can you assess your reliability? You AI, can you give me a notion of confidence and reliability? This is a field that has tremendous research activity behind it, because we know every time we deploy these systems for high risk decisions or real-time decisions, self-driving cars, this is very important to be able to improve the uncertainty quantification of the AI models. So this is what we call the assurance stack, which is a key component in our research. Uncertainty quantification, verification, validation, and validation for the data, for how the model was trained, the model itself, and how the design of the model is done. Explainability and interpretability. There are several applications in which we don't only care about a decision or an opinion, but we want the system to be able to explain how it arrived to that decision. The biomedical field is very important. Yes, you can make a medical diagnosis, but when a doctor talks to another doctor and they share opinions, they articulate, this is why I reached this specific differential diagnosis versus something else. We would like the same to be able to be done with the AI models. And there is a difference between explainability and interpretability. There is also causality. With big data, correlation is the driving force, but correlation does not imply causality. And often in decisions we make, we need to have causality established. Right now, this is another area where there are a lot of progress, but still AI is lagging. Robustness, adversarial attacks. These are models that are trained with data. Therefore, they are trained with things that have happened, things that exist. They cannot necessarily learn things that have not happened yet. So how can we prepare these systems for these unforeseen circumstances or for intentional adversarial attacks? And of course, dealing with bias and regulatory aspects. Bias, I'm sure you know that. If you train a system with biased data, the response will be biased. We've seen that in anything related to equality, DEI, with face recognition. I'm sure you've seen the narrative and the different studies that have demonstrated that you throw in a lot of biased data in, you will take a biased model out. And we need to be aware of that, to regulate, control, to look at our data early on before we feed it into any training model. And of course, regulatory aspects which I will discuss later on. In the interest of time, I will zoom through those slides and say, okay, we have applications in material sciences where it takes atomic modeling data and the AI is used to predict material properties. We're also using AI to design new materials. We have applications in advanced manufacturing where AI is used to detect defects. We have applications in anything related to imagery. Think about satellite images, and we develop AI models that are somehow multi-purpose. They can cross from one domain to another with the transfer learning concept that I discussed earlier. And this is an area that exploded during the COVID pandemic, where the language models, which started for language, they were then transferred into chemical compounds to do drug discovery, basically designing new molecules that would be potential therapeutic targets for COVID. And we can take that concept, of course, this workflow, this scientific workflow that can be applied for other diseases and other conditions. A lot of these activities happened on the Summit supercomputer during COVID, and we will see continuous growth of this particular application domain because of the increased concerns for biopreparedness, for potentially another pandemic, how we can pivot fast and accelerate the discovery of therapeutic targets. This is the second phase of the previous work that I presented. Often these AI models are always designed with the intent to optimize something, right? When you develop a new molecule that you believe that is going to be an effective therapeutic target, this is one aspect of the story. The other side of the story can be effective, but it can be also very toxic. So there's also toxicity. So how you can have multi-objective optimizations within the same AI model. That speaks to that. This is AI to create conditions, stress conditions for AI. So how we can use AI to develop adversarial scenarios for an already developed AI model so that we can identify places of potential failure. So we have developed a model, but we cannot just deploy it in the real world and see where it will fail, where it will not fail. Can we use another AI model to create these adversarial scenarios and completely in silico test the first model and see where it fails and if there is areas that we need to improve, particularly for scenarios that have not been experienced before, there is not enough data and these circumstances. And some of these technologies we develop, of course, they are licensed, such as this technology that was licensed by General Motors, and it has to do with the design, vehicle technology and design, particularly with driver assistance systems. So this is the fun of working at the Oak Ridge National Lab because it's multidisciplinary and it is also a lab that focuses a lot on translational science. So if you like to do science at the very basic level, do basic sciences, but you can also follow the translation of that technology to the real world. And I find that extremely fascinating. This is a project that we've been working with the National Cancer Institute for years now. And this is very close to my heart as the PI. We have been developing and deploying AI solutions to modernize the National Cancer Surveillance Program. Cancer is a reportable disease. Every cancer that is diagnosed in the US is reported in a database and then followed for several years. All of that information becomes part of an epidemiological database that is given to the scientific community to do further epidemiological studies. It takes so much time to collect the data and curate the data that typically the epidemiological data that is available now, it is already 2 years old. So how we can accelerate and do near real-time cancer surveillance, we are deploying different artificial intelligence models across the cancer registries in the US, and we have accelerated this pipeline to down to 30 days. And this is truly impressive when you develop new therapeutics, they are deployed in the community, and you try to capture fast the broader effectiveness of new diagnostic systems or the new therapies. This is why all of these applications, they are just built on each other. And another one that speaks a little bit to what I call computer-assisted serendipity. What if we take the whole biomedical literature and we develop an AI model that captures and codes the relationships among the different medical concepts the way they have been documented in the literature, and then we layer it with an AI model that does scientific hypothesis generation. Can you traverse these connections and find new connections that would be worthy of exploration? So that is the aha moment that I call computer-assisted serendipity. I have to speak a little bit about health because I said it's close to my heart, and I believe this is an area, as much as we talk about assistants and Alexa and this and that, there's so much happening with AI in medicine. This is the most fertile field for R&D. And already in your day-to-day operations with physicians, AI is part of their workflow, either because there is virtually introduced in terms of, design scheduling or interpreting different diagnostic tests and medical images, or being part of something very physical in terms of the different robots for surgery. And these applications exist, and we will continue to see many applications in some of the areas that I've highlighted there. Disease diagnosis, drug development, personalized treatment, telemedicine, of course, and we will continue to see growth in gene editing. Of course, the question is, why this particular application domain is so fertile for AI, and do we really like that, right? Because it's the personal relationship with our doctor, the expert. Are we introducing a threat? The reality is that there is an urgency in medicine, and it is often unrecognized. And it goes back to, we have growing shortages in healthcare providers. That is given. We also have an aging population that the majority of us will have to deal with at least one of the three diseases: cancer, Alzheimer's, or heart disease, because age is the #1 risk factor. This is true for all of us. There is a data overload, data waste, there is medical error. So how can we use AI to help the medical practitioners improve their productivity, improve their performance, reduce fatigue? If we have very few of them, we need to make sure that the fatigue and workload is managed appropriately, and how we can help them meet the critical demand that exists among the patients. This is why we see a lot of AI in medicine. But now, wearing more the scientific hat, I have to say that I've been doing this latter path for many decades in terms of the problem is presented, the medical condition is presented. What can we do to address it with an AI model or whatever it is? But when we look into our future, we need to be thinking that maybe when we start intervening when the condition has appeared, maybe it's too late. The only thing we're prolonging is life with a problem. We're not necessarily prolonging quality of life. So is there something we can do earlier on? And what would that be? Well, what that would be is that if we live in the era of generating so much data and so early on in our lives, why not start modeling our wellness, our well-being from early on, and create that individual digital twin? Every time more data that is generated, a new medical study, that becomes part of the model that needs to be updated accordingly. And if we have that digital twin, what would that mean? That means that our next visit with the doctor, or even if we had it on our own laptop or iPhone, we can say that this is how my trajectory is at that point of entry in life, or point of entry at some or whatever point we start monitoring this. Then I can start playing with this digital twin. What if scenarios? What if I develop these kinds of eating habits or lifestyle choices? Or if I relocate in an area where the environmental factors are of a certain type? What would that mean for me, for my personal life trajectory? And if I have that life trajectory, maybe I can intervene early with choices that I can make to change my trajectory, even if it is to delay the onset of a condition that genetically I'm determined to get. So I don't know if this will happen in my lifetime, but this is actually a dream for me, that we will be able to generate that, and absolutely artificial intelligence will play a role, because in order to develop this very complex model of physical biochemical processes, for some things we know and many things we don't know, and we will have to use data and AI as surrogate models to plug holes and gaps that exist. But the more we work towards this space, the more we have access to big computers to make higher fidelity models, the better we will be towards this, which I consider truly a technology that will empower us as patients.
You have your own avatar, right?
Exactly. So the final thoughts for those who were debating whether it is AI is transformational, I think this third wave of AI is the most transformational of all. There is a very interesting article that appeared in The Economist this month, and it talks about what are the key characteristics of an innovative technology used in many industries. I show you examples. Check. Inherent potential for continuing improvement. I showed you the improvement over the past 10 years. Check. And give rise to innovational complementarity applications that transfer into other areas. And we've seen the transfer learning happening. And it will have a broader impact in terms of we will see more applications where we need more prediction power, predicting weather events earlier and with higher accuracy, increase the speed of predictions for near real-time deployment. But now, whether we will leave the judgment to humans, we still need to rely on humans to make the final judgment, and that is not a bad thing. In science, let's go back to the if-then statements. There is a place for AI. AI is not going to solve everything and not necessarily lead to the best solutions. It all depends on what is the nature of computations that is required. If we have too many exceptions, too many rules, AI has a role. And if the algorithms are too complex and too inefficient, then AI has a role. But AI is not the panacea. Then it should be considered as a solution, and that's what we see right now with the scientific community. Scientific challenges, we still need to develop models that learn with limited data. Some of the most challenging problems are problems for which we don't know much, so we don't have enough data. Think about rare diseases. Learning with noisy data, definitely the data we collect is dirty data. Learning to foresee the unseen. There are always going to be events that have not happened in the past. So how is AI managing that? And of course, talking about explainability, uncertainty quantification, and causality. These will remain strong scientific themes for AI in the next decade. We cannot underestimate challenges with infrastructure and policy. In order to be able to do all that, continuous investment in computational power is extremely important. Understanding how to collect and manage heterogeneous data is very important. Being pragmatic, that data is the currency of the 21st century. Entities, enterprises do not want to share data easily because that's what makes them unique, not necessarily the AI algorithm, is what the algorithm has been trained with. So for entities such as, let's say, the biomedical communities, where there are sensitivities about the data, sharing is not easy. Proprietary data is not easy to share. So we are working as a community to develop models of collaboration, which we call federated learning and privacy-preserving learning. So the individuals do not share data, but they share model parameters among them. So we at least can accelerate progress. And last but not least, we should not underestimate that AI requires a lot of power. So just deploying AI and training big models in a blind way, that is not socially responsible. So continuous innovation towards algorithms that are more energy efficient, not only hardware that is energy efficient, is extremely important. Ethical and legal issues, of course, these technologies, they impact our lives. They need to be regulated the same way with, drugs are regulated. So there is a, sorry, can you go back? I clicked by accident. So this is something that is part of the conversation. And then there's certainly a lot of reluctance among users because of the fear that they will be replaced. And I found this line in an article that says, these recent advances in AI will surely usher in a period of hardship and economic pain for some whose jobs are directly impacted and who find it hard to adapt. The graphic designer example that I gave you is such an example. Another example is that often it's not the specific job that can be threatened directly by AI, but it can be threatened by a new economy that is created. Think about Google Maps. Google Maps were introduced to help taxi drivers, their job, and make them more efficient. But what happened? They also generated a whole new industry, Uber, Lyft, all the individuals who said, oh, I can do that too, because I have this assistant. So we don't know about these unintended consequences of AI. There will be. And policy, cybersecurity concerns. We can steal data, we can hack data, we can hack models and make them change the response they give and do it intentionally. Benchmarking of data quality and algorithms is extremely important because we need to have transparency as a community. And of course, there will be, and there are already in some cases, state and federal regulations. Certainly, Europe is further along on this than we are. So my last slide is that the hope, what I call the hope, the hype, and hard truth. There is always this with any disruptive technology. The hope is that we will be able to enable the automation of functional knowledge. Actually, believe we have done this already. And there will be lots of successful applications. We've seen lots of successful applications and more emerge. There is still no hype that AI is more powerful than the collective intelligence of experts. No. Experts, of course, can make mistakes, but AI can also fail catastrophically. The practical translation of these tools is straightforward. It is not. And medicine has proven that just because you create an AI model, you have to educate the user how to use it responsibly. And correlation is enough when big data is involved. This is a hype. Causality will remain at the core of need for AI. The hard truth, we need to continue to invest on infrastructure. The big leap happened 10 years ago because there were some dramatic improvements in infrastructure in terms of big computers, new hardware, and being able to capture the data. The human in the loop will remain a challenge for the translation of these tools because they are always, more often than not, and for critical applications, they will be used by a human with a human. Interpretability and uncertainty will remain important to build the confidence for using these systems. And last but not least, vulnerability. There is lots of vulnerability with these models because they can be reversed engineered, they can be hacked. I will say there is lots of vulnerability with us, the users, because there is also cognitive hacking. And it goes back to the notion that if you give someone a stick to walk, they may forget how to walk. And we don't want to reach that point of being unable to think for ourselves. So my line that I have given in many other presentations, it is our responsibility to be informed consumers of AI technology. We should not be fearful of the technology, but we should also be critical of how it was developed, how it is deployed, and what is our responsibility to use it effectively. So with this, thank you very much.
We have several questions on Zoom, but I think all of them have been addressed by, they were written, mostly written during the talk, and I think you've addressed most of them. The last one I find a bit amusing.
Yes.
Trent Prim says, my doctor won't even use email. Seriously, how do you convince the medical community to use technology?
Well, actually, the doctor, I'm married to a physician, so I understand the jokes about doctors. The doctor may not be aware that AI is already part of their workflow, because a lot of scheduling happens with AI. And to go back to a more specific medical example that, again, from breast imaging, these days, the majority of breast cancer screening studies that are done that are automatically read by AI. So the results that are presented to the radiologists are not only the image, but also the opinion of the AI system. AI is used to highlight blood flow in EKGs and other studies. So it's already part of their day-to-day operation. Now, there may be other reasons why the physician doesn't want to use the email, but I will not address that. And certainly, let's not underestimate the generational gap, right? We're talking about, when I was a graduate student in the early stages of my career, and I was doing a lot of human-computer interaction, it was very obvious, all the studies that we were doing to evaluate the impact of AI on the radiologist's performance, the younger generation, they were, yeah, sure, let's play, let's do, let's. The older generation, they did not want to touch that system. The system was unfriendly to them. Maybe it was threatened, they were threatened. Maybe the whole technology, the digital revolution was a heavy lift for the older generation. But now we're talking about our children, that's all they know. They cannot operate without digital devices. I think there is a joke at Twitter where you show the phone, the rotary phone, and say, can you dial? And they look at it and say, are you joking me? What am I supposed to do with this? Where are the buttons? So this is a new era, and our children are better versed in technology, and they expect these challenges. Some of the research I was doing before, and I haven't followed through over the years because, you know, moving from Duke to here, was I wanted AI technology to train the next generation of physicians, because the model of training for physicians is the apprentice model, right? I sit right next to the physician, and the physician tells me, oh, this is how I interpret the image. That's what some are very good communicators, some are not. There are not as many physicians to do that education. So imagine if you can design an AI model, a game for this new generation that tests them through the process, identifies the area of weakness, and introduces cases that are more similar to the areas where they have personal weaknesses, just like playing a game. When you're ready, you will move to the next level because the system has recognized that you have mastered this thing, and you go to the next level and the next level. So these are the creative ways that we can use the technology to enable the next generation of physicians. And there are lots of applications out there that individuals are working, they are fun. It's just that some of the highlights I showed you, text to image, they attract a lot of attention because they are entertaining. But actually that text to image, there is the reverse, image to text. You can give it a medical image to AI and it create the radiologist note. The same way they will look at the image and they will dictate on the file what they've seen. You can have an AI model take the first cut of the description.
I'm curious about error correction. Suppose you get the wrong answer, like the bear can live on the moon. How do you slap it on the wrist and fix it? Do you load more data or do you change an algorithm?
So this is a very interesting question for a different reason. Yes, you have to, that's why interpretability is very important, because you need to build it in the AI model to tell you why it reached that decision, because it gives you a glimpse of what went wrong. Absolutely more data, and that's how you refine the algorithm. What is a bit alarming with the technology, the way it moves right now, and that may be controversial opinion for the audience. All of the previous waves in AI were dominated by academia. They were truly a scientific endeavor. The last wave is dominated by industry. Industry, Google and these companies, they have lots of data that the rest of the community doesn't have available. So they can create these large scale models and then they share them with the community. And the community can take them and do the fine tuning. That's one example that I give you. I can start with a general model and then I have my precious bucket of biomedical data. I can fine tune the model and I have something that really works and I enjoy it. But I have no insights about the initial model. What kind of data it was trained on, what kind of biases it may have. I have to do that in the later stage. One of the activities that we hope to enable with the Frontier supercomputer is that to bring together the scientific community to train from scratch these large-scale AI models with scientific data. Train them from scratch, train them collaboratively as a community, because that will be a different type of enabler for the scientific activities we have. This is an area that we're working on, particularly when I discussed about federated learning. Coming from the biomedical community, I'm not naive to expect that people will share data, scientists will share data openly. But if we, in the leadership computing facility, we create that framework of federated learning so that they can collaborate on the big computer without crossing the data boundaries, just sharing models, that's good enough. That's a win. And that's something we're working on, actually.
So first of all, I was intrigued at the possibility that I could use ChatGPT to write the minutes for these meetings. Until I heard about the bears on the moon. But a more serious reaction I had is the intersection of noisy data and causality in sort of large behavioral complexes, which you mentioned is a challenge for AI, but is also very challenging in the human environment.
That brings to another philosophical question that was posed in all of these debates that happen with AI. Do we really want to mimic human behavior? That's what I enjoy about artificial intelligence, all of these philosophical debates that it brings, and because you can make an argument for one or another. The noisy data is important for us because on one hand, we need a lot of data to train the models, but the data that exists available, and it is the easiest lift, are noisy data, right? Nobody sits there to curate them, clean them, everything. But there is a price to be paid with noisy data. The quality of the models, and we have seen with studies that more noisy data can be as good as less clean data. But the reality is that still it takes a lot of effort to clean the data, so go for more and more, right? That's where it is. That's how we've seen that trade-off play out right now in the past decade. We're also thinking about AI curating data, of course, right? That's another thing, Shane, we should do that.
There's a lot of concern in the educational community about chat GPT.
Yes.
But is the educational industry applying AI? Are you aware of cases where they've tried to turn that around and basically say, here we can use AI to assist students forward? I mean, is someone practically selling that today?
I am not familiar with that, of course.
AI to find out if it's cheating. We've already found that on everything.
That these tools exist, right? And it's very similar to the example of the adversarial use and understanding, being able or implementing a Turing test. Is it real or is it ChatGPT? Because I'm sure that would be a good study. If we have a lot of data of trying ChatGPT versus a human, and then you develop another classifier that says, was that the response of a ChatGPT model or was it truly a human? Because clearly the structure, it is certain structure, and with other times that I played with ChatGPT, where I gave similar but related questions, I noticed that it was following the same structure. It was just doing plug and play. So there are certain essays, a certain format of essays that it goes back to and repurposes.
My doctor is Google, and he always answers when I ask him the question. But the question comes back to the same we were talking about here. What you have to then yourself decide what the right answer is, and it is the best answer. Is Google working on, sort of their AI part of this to have a bunch of doctors sit down and answer the question for you?
I cannot speak to that. Certainly, industry has courted for years the medical community for data acquisition and for knowledge acquisition. In the past, there have been lots of challenges, legal implications. And because the question is, if an industry, let's not say Google, develops an AI model that leverages data from Duke University, right? Or the expertise of physicians from, who owns the model and who owns the profits? The person who developed the algorithm, the person who provided the expertise, the physicians, or the patients who contributed their data. That's part of the policy and legal implications. And right. So
Do you have suggested reading for us?
on
Yeah.
the vast field of AI, yes, but it would help me if there is a particular flavor because there is so much. Sure. I can send a few higher level readings about the state of AI, the biomedical field. I guess I can email to you and you can distribute it.
I'm also curious about the bears on the moon suggestion, because presumably the system had all sorts of data at hand to say why that would be impossible. Is it a matter of interpreting your request as wanting a fantasy or science fiction or something?
I have no clue, and
It's important because I know there's a lot of concern about promulgating misinformation, conspiracy theories and election fraud, whatever.
oh, that is actually very much a concern
Yeah.
with these kind of technologies. Absolutely.
Was assuming it's the wrong answer.
Yeah, you're absolutely right.
Other things you're not going to know that.
You're absolutely right. It will be impossible to tell who's writing, who's responding, and all of these things. No, I don't have an answer. And I have to say that I am one of those individuals who's fascinated with the technology. And I try to do, scientific hypothesis generation by trying different examples. It's just that ChatGPT is bombarded, and most times it's like, I'm busy now, come back later.
Well, I think the time is up, and we thank. Let's thank you presented for us. Thank you.
Thank you. I appreciate the opportunity.
All right, we appreciate you coming out here.
Yeah.
Well, excuse me, I need to be at 2 o'clock at the lab.